Thank you very much. I would like to thank you very much, the organizers of the workshop and of this project, for inviting me to this nice workshop. It was very nice to hear Akira as well before. So I'm going to switch gears quite a bit with respect to the previous presentation. So I'm going to be talking in this talk a lot about, it's going to be really at the interface between physics and computer science. So it's going to be quite a bit of protocols and all sorts of different protocols for cryptography, communication complexity, and up to a computational advantage. So I guess here, as the title says, it's a little bit of an approach to look at quantum technologies and what we can do with photonic systems in the relatively near term before a universal and fault-tolerant quantum computer like the one that Akira was talking about becomes available. So cases and instances and tasks for which we can demonstrate a quantum advantage. So I'm going to be using all sorts of different techniques, discrete variable, continuous variable, but I'm going to be mostly focusing in big part of this talk about the more recent work that is a little bit of an intermediate situation where we're using, I wouldn't call it non-Gaussian, but it's a kind of a combination, it's a platform where we're using coherent states and single photon detection. So I'm going to explain why we're using this technology. So let me start. So the general context of this talk is quantum communication networks and what we can do with them. So I'm going to be using in general photonic resources, mostly in optical fiber propagation. And of course, the general context is that one can do information processing with network nodes. And I imagine here the network in a sense where we have servers, clients, memories, all sorts of devices that need to be connected and that we would like to use for performing specific tasks. So I'm mostly interested in the security and in the efficiency aspects of such a network and how to preserve it in situations where security matters or that privacy matters. Okay, so we're going to come back to this a little bit notions that are more application oriented on how you deal with malicious parties, untrusted parties in a network, and what you can do to provably demonstrate in quantum advantage even in such situations for communication, for a big range of communication and computing tasks. So I'm going to go through first relatively quickly, just a little bit of an overview of some mostly cryptographic tasks that we're looking at in my group. So this is going to be just an overview. I'm not going to go into the details, and then I'm going to go into more details in things that are beyond cryptography, that are more about the efficiency, and then with a specific application to even a computational advantage that we have shown recently with our experimental platform. So let me start with cryptography. So what is the very first thing that and the most ubiquitous, let's say, in quantum communication that one would like to do with such a network? It would be to secure the network links. And this, of course, can be achieved with quantum key distribution. So a little reminder here for everyone, since we're not in a cryptography conference, that quantum key distribution provides a future-proof information theoretic secure solution to the key agreement problem for secure message exchange between two trusted parties. So there is a lot of work happening today on QKD. There is a bunch of challenges that are being addressed by the community. That includes photonic network, cryptographic integration, beating losses, and of course taking care of the untrusted nodes, either by using repeaters, repeater techniques, like the ones that were mentioned several times in the workshop, and also and of course satellite communications. So in our group, just a little overview, we're focusing on this point of view on coherent state continuous variable QKD in all of these aspects. So this is very much Gaussian. Okay, as you know, to do anything with quantum key distribution, you don't really need, and this is quite a striking difference with respect to other more going into the computing regime for continuous variables is that one can do quantum communication and protocol like this with purely Gaussian techniques. So starting in our case, we're working with coherent states, and then we're doing homodyne and heterodyne detection, and we're addressing with our work all sorts of these different challenges that you see here, from feasibility studies to feasibility studies on a satellite to ground scenario that you see here on the slide, to chips, silicon photonic chips for CVQKD, and also integration into coherent telecom systems. So what is the link here? I would say that these techniques could potentially, some of these techniques that are being developed for continuous variable QKD could find potentially applications in continuous variable efforts for error correction and computing as well. So keeping an eye between the communities is extremely important. I'm going to move on now to a few other cryptographic tasks where in different security models where we need to consider, for example, malicious partners, and there it opens the door to many more functionalities which can be interesting for general networks, and they provide typically a nice framework for demonstrating quantum advantage in security. Okay, so there is a selection of protocols that you see here. They look a bit like a catalog, but actually each one of them is very important for achieving specific complex, more and more increasingly complex tasks in a network. And when it comes to physicists like us talking with computer scientists that have worked on this type of protocols for many years, but these protocols are very abstract or use very unreachable, so very inaccessible technologies. It's to close the gap between these protocols and what can actually be shown in practice and rigorously. So this is something that I've been doing for years now, and this also affects, basically goes throughout the whole all the type of work that I'm going to talk to you about today. So you start with an abstract protocol that uses resources that are typically not what we can which out of reach with state-of-the-art technology, and are also very typically vulnerable to imperfections, and make them realistic and implementable today. And then another point that I would like to stress out when one goes up to the protocol implementation, and not only at the component and level, is that extreme care needs to be taken when we claim a quantum advantage. Sometimes it's tempting to claim it a bit too quickly, and it's important to perform a fair comparison with classical resources. And this is also something that has been sometimes neglected in this field, and it's particularly important to consider it when we're showing or when we're demonstrating this type of protocols. So I'm going to show you a couple of examples. So one of the protocols that we have worked on is the so-called coin flipping. So this is a fundamental primitive that we can find, for example, in networks for distributed computing applications. The idea here is to allow two distrustful parties to agree on a random bit, and you would like, ideally, if the coin flipping is unbiased, to have a zero bias, okay, to not have any preference for each one of the coin sides. And so this has been known for quite a while. And what has happened is that typically, as I was saying before, this type of protocols were inaccessible for experimentalists because they relied on high-dimensional quantum systems, or on measurements that are not accessible, etc. So the very first thing we did is to perform a theoretical analysis that allows, for example, to include imperfections. Okay, and this essentially means that you have to allow the participants in this protocol to allow for an honest abort, okay, to abort the protocol in case, even if they perform honestly the protocol, and this has to be allowed up to a certain degree. So what we showed a few years ago with this type of protocol is that that looks a lot experimentally like a discrete variable QKD plug and play system with specific, of course, it was harder to do than a typical QKD system because we needed to work with average photon number pulse per pulse that was much, much lower than you can find usually in QKD systems to ensure the security. And with this type of system, we saw the quantum advantage from metropolitan distances. So you see here the proof of the quantum advantage is that cheating probability that you see here is smaller than what you would get with a classical bound. So it's the purple zone that shows the quantum advantage with respect to this line, this black line that shows what would be classically possible with the same resources. And this is plotted as a function of the honest abort probability because exactly it shows to you the importance of considering such imperfections. And so more recently, we have come up with an experimental proposal to perform a stronger form of coin flipping, which is called weak. This is the funny thing. Although it's a stronger form, it's actually called weak coin flipping. And so with a heralded single photons, and this is actually right now under implementation in our laboratory to extend even more this type of implementation. Another example is quantum money. So quantum money is a cryptographic protocol that was actually came before even QKD. It's based on the very initial idea of Wisner about using, in general, the uncertainty principle for security. Many protocols had been proposed before, but they all needed several rounds of quantum transmission and verification, and they were all not robust to imperfections. When I say not robust to imperfections, I mean that for example, if you included dark counts in the detectors or some sort of losses, then the security would break down. Okay, so this was considered very hard to implement. So here as well, our approach was to propose a protocol that can live with classical verification and can also be function with states that we find, for example, in typical BB84 scenario, and where you have three parties that participate in this quantum money protocol: the bank, the client, and the vendor, and you perform these challenge questions. And the idea here is to provide a security guarantee to the vendor against a malevolent client, okay, a malicious client who may want to duplicate the quantum money that he has in the form of qubits. So with the experimental setup that was based on polarization and coding, we showed here as well the secure region of operation with for this type of protocol, where again you show here how you prove the quantum advantage here is that you show that the probability of answering the bank's challenge correctly is bigger than what you would find in a classical scenario. So it's all a matter of, again, making sure that the experimental conditions are such that you can prove rigorously unforgeability. Okay, and so now currently we're extending this protocol. Normally, when you do quantum money, you would like your quantum states naturally to be stored into quantum memory and be used on demand for a transaction of quantum money. So we're working right now with Julian's group to implement this quantum money protocol as well, using a real quantum memory. And I like this because it's kind of a neat use of quantum memories in cryptographic scenarios, and not only in quantum repeater type networks. The final example I wanted to give before moving on with beyond cryptography is quantum network protocol. So this is a big line of work that we have done, where we basically consider multipartite entangled states as an important resource, as a fundamental resource for quantum networks. And for the demonstration of advanced applications. So what we have done is we have done a series of works where first we propose theoretically how a set of users that share a multipartite entangled state, for example, in particular a GAZ state, they can verify the presence of the use of this type of multi-party entanglement, even in the presence of dishonest parties. So the security guarantee here is that the honest parties are sure to use the correct state despite the presence of malevolent, of malicious parties in the network, which can also collude with the source by strictly bounding the probability, basically by alternating randomly test rounds and use rounds, and by formally proving that in the test round that the verification test that you use passes the test, then they can have a certain guarantee, which is, as always in cryptography, epsilon bounded, with some epsilon that has to be very small, to be the correct state. And of course, this bound depends on the fidelity of the state, of the multi-party entangled state. It depends also on the losses in the system, because as always in this type of protocols, malicious parties can take advantage of losses in the system. And so we showed in this work that you need very high fidelity resources, and also you can, for the moment, the protocol can have quite small loss tolerance. In this work, we show that it cannot tolerate more than about 5% of losses. So you have to do some sort of post-selection to ignore the detection losses in the system. So these are what I'd like to stress here is that there is a different thing to say, I have done an entangled photon source, a multi-party entangled photon source, which by default is an extremely nice thing and to show, and a different thing to say, I have used my multi-party entangled photon source for a specific application, and I have proven the quantum advantages for a specific task with this source, and the gap can be very big sometimes, and by doing protocols, this gives us also feedback on the and this is extremely important, on the qualities that our sources have to actually be relevant for true applications. And I think this is very important to stress here, and it applies to pretty much all components and systems across quantum communication and computing technologies. So to go further than this, so we have also found an application of our verification protocol to anonymous message transmission, which is a specific quantum network protocol, where the verification phase here guarantees the anonymity of the message transmission. This also needs very high fidelity, and it's actually right now we're in the process of building a multi-party entanglement source. So this is discrete variable type of sources in our lab, so fusion-based post-selected entanglement, just so that we make sure we're talking about the same correct resources to perform this anonymous message transmission. And I will add here that we have also come up with a theoretical framework to show composability, which is important for further application. Composability here means that you can pull together, compile cryptographic protocols one after the other, and basically use the output of one protocol to a next one, and without losing the security. You can sort of, so you add the epsilons throughout the computation or the communication task, which allows you to progress in the calculation that you want to perform. So this is kind of the overview, the general overview that I wanted to give on this type of more cryptographically related protocols. So I didn't go into the details. We can, if you would like to ask more information, don't hesitate at all. I would like to pass now in a different type of protocols that are called communication complexity. So this is a quantum advantage in communication resources. I'm going to explain here a little bit the notion, because it's not widely known in general in the physics community. So here, what we're talking about communication complexity, what we're interested in is that we have again our two parties in a network, and the output now, they have, each one of them has an input, receives an input, and the goal is to output the function of these two inputs with minimum communication. Okay, so the communication complexity studies the amount of communication required for distant parties to jointly perform a distributed task. Okay, so this is the premise of what we want to do. And for those of you who are specialists in the matter, I should also specify that this, in our setting, this is a randomized setting where this happens with a small error probability. So we're not looking for absolute absolute communication complexity, minimal, we're allowing for a particular error probability, and the whole point is going to be able to show a quantum advantage with a small error probability, as small as possible. So there is a big number of applications going to VLSI design, data structure, secure computation. So there is a big range of applications where one will want to minimize the communication between two parties. An important distinction that I need to make here as well is a distinction, because it's particularly relevant for the quantum advantage that we have shown, is the distinction between transmitted information and communication time, which are not necessarily the same thing. So the communication time, I think it's easy for everyone to understand, is the amount of time required for the parties to perform this distributed task, okay? The transmitted information is a little bit more subtle. It is information contained on the inputs, about the inputs that the two parties have received, in the total messages that have been communicated by the parties. And why am I saying this? This is not the same thing, right? For example, if I send to Bob the same message all the time, during their communication that is independent of the input, then the communication time is going to be the same, but the transmitted information is going to be 0, right? So it's important to clarify that there is a difference between these two. And I should say the transmitted information has a particular value in privacy. When it comes to privacy, achieving privacy and caring about privacy in networks, because essentially it tells you how much information about your input you actually want to reveal, okay? And so this is where typically it comes into the picture, and I'm going to come back to this point later when I'm going to be talking to you about the computational advantage that we have shown, where, for instance, in cryptography, there is techniques like zero knowledge proofs and things like that, where you are trying to perform a task with revealing as little information about your inputs as possible. So this is why transmitted information is important. So let me show you now a specific protocol in communication complexity that has been known for several years now in the computer science community, because it shows an exponential advantage between classical and quantum resources. So what is this hidden matching protocol? We have Alice and Bob. Each one of them, as we said, have an input, okay? So Alice's input is a string, a bit string. She sends a message to Bob, and Bob has as an input what is called a tuple, okay, so a matching. This is why this is called a matching. You see here an example of a family, of an M4 family, which has 3 possible matchings, and his goal of this protocol is to find out, to select one of these matchings, and one tuple out of one of these matchings, and find the parity value between the 2 bits inside the Alice's string that correspond to this particular tuple. So it sounds, for us as physicists, it doesn't sound particularly interesting, but it turns out that this is a kind of an important problem that appears in computer science, quite useful for many applications, and as you are going to see later, it's going to be even more useful for specific things that we want to do. And quite importantly, it was shown as one of the very first communication complexity problems that for which there is a known exponential advantage. Okay, as you see here, that the classical resources are square root of n, which is the size of the input, while it's log n in the quantum resources. I should also point out here, for the theorists among you, that this is one-way communication. This is important. Otherwise, the two-way communication is a big resource. So we only have, Alice is the only one that can communicate information to Bob. Otherwise, the solution to the problem is trivial. So let's go now a little bit to how one would like to demonstrate this protocol in practice. So this gap, as all gaps in quantum information science, is extremely hard to demonstrate. Why? Because typically, you need these input states, these high-dimensional input states that are called fingerprints, that you see here. These are the quantum the quantum fingerprint states. You can imagine here, if you visualize these states as a physicist with a very large input size in the hundreds or the thousands, this is what is needed to actually demonstrate the quantum advantage in practice, because for several reasons, there is quite a few prefactors in there to demonstrate your soundness, that it actually works, your protocol. And so this would mean that you would need either single photon states across a very, very big number of modes, or log n entangled qubits, which is out of reach currently. Okay, so these quantum fingerprint states are considered, were considered for a long time out of reach, and this is why these protocols have been kind of in a dormant state. So now, a few years ago, there is this coherent state mapping that was proposed, that was coming from Norbert Lueckenhuisen's group in Waterloo, which is actually quite interesting, because what does it show? It shows that you can take these fingerprint states and actually translate them to this coherent state mapping, where basically what they showed in their work is that you can take these states that you see here, a train basically of coherent states, with a total mean photon number, alpha square, spread across all time and time modes. So that's why you have very big trains of coherent states. And this spans a Hilbert space that is equivalent to the alpha square log n qubits that you would need to perform your protocol. And so what has been shown in this work is that actually this exponential gap that we saw before that appears in hidden matching, it's actually preserved with this coherent state mapping for the transmitted information. That's why I made the distinction before, but not for the communication time, which is the same, becomes linear, right? Because obviously you need to send all these coherent states, so therefore you don't gain in time. You don't gain in time, but you do gain, unless, although there is some recent work on multiplexing techniques for gaining also coming back to time, but this is, let's keep it now for the moment to the transmitted information. And so you preserve this exponential gap in this case. So this opens the door, by doing this, you open the door to implementations that involve what? Involve an experimental platform where you can use coherent states, linear optical circuits, simply for transferring, manipulating your photons, your coherent states, and single photon detection. So this platform, as soon as it was proposed, it was used quite quickly for experimental fingerprinting, okay, quantum fingerprinting. So by basically interfering these trains of coherent pulses, I'm going to show you examples afterwards. So this was done, for example, from Jian Wei Pan's group in China and in Toronto. And very recently, by the way, we have extended this fingerprinting to a task relevant for machine learning. And so with vectors, the comparison of vectors, I'm not going to show the results here because they're really, really very fresh out of the lab. So they need to be validated, but there is quite a few things that one can do with this type of system. But if I go now back to my communication complexity problem in hidden matching, is this sufficient to allow me to perform the implementation? So if you look at it, you will see that you have, for example, Alice that will be sending now her input. Remember in this protocol, the input was these states here. Okay, you don't need anymore this very large entangled photon state, so you can just send trains of coherent pulses. But is this sufficient to make it implementable? And then Bob needs to pick the matching. So the thing is that this is not enough, right? Because depending on the matching that Bob gets, these pulses here, they can be very, very, very far away in your train. So you need all sorts of different switches and delays. And when we're talking about 100 or 1,000 input size, this still becomes overwhelming for very large N. So there is still a blocking point here. This is not sufficient to actually experimentally show the quantum advantage for this protocol. So what we did is we changed this and we applied what is called sampling matching, what we call it sampling matching, where we changed slightly the protocol. And this was nicely, it's actually nice to see how the fields fit together, because by looking at this problem, this was inspired, the solution that you see here was inspired by a very clever implementation for a totally different field. For those of you who know a bit of QKD, in the differential phase shift, round robin differential phase shift QKD, that I saw in some paper totally randomly. I was like, this could be applied to our problem, okay? And then we had to go, of course, with my computer science colleagues through the rigorous proof to show that it was exactly equivalent. So what is the subtle difference here that allowed us to show this is that you input, Alice receives her input string, but Bob doesn't receive anymore the string on the matching thing. All he has to do is to perform interfere Alice's coherent state with his own, okay? He gets interference events, and then whenever he has enough to perform that are sufficient to pick a specific matching that he chooses, then he can produce the parity that is requested. So it's a kind of sampling. That's why we call it sampling among all the different matchings. So for this to work, again, we need one-way communication, and also we need to make strictly sure that there is a uniform distribution of this matching with respect to the message that Alice sent to Bob. So the question now is a little bit different. So given this input from Alice, what is the transmitted information needed for Bob to output the parity of this tuple from a uniform matching set with a success probability, remember we're in a randomized setting, that is equal to 1 minus delta. Okay, so this is our delta parameter that shows how good we are in terms of application. So we showed for this protocol that the exponential gap in transmitted information still holds, okay? And we also showed how to show it experimentally. So again, we have our Alice's and Bob's pulses that are being interfered with this sampling matching scheme with on the single photon detectors, and there is an additional element here that comes into the picture, this phi parameter here, which is an additional phase that you want to add so that you hide the information. As we said before, Bob should not be in a position to find all the inputs of Alice. We want him only to find out the parity information. Okay, this is important. Again, remember about privacy issues. Okay, so this is important. We don't want him to know all the bits, just the parity. And so by hiding by hiding this extra phase parameter, we hide the bit information, and all is needed by detecting the single photon events here. He can recover the parity that he wants for this specific matching, but not the bits themselves. So this is how the experimental setup looks like. There is a phase correction loop coming. I should also point out that this is a proof of principle implementation in the sense that Alice's and Bob's pulses come from the same laser and not from separate lasers that normally in this type of scenarios it should be the case. So this is a common arrangement that all of these, up till now, many of these works are doing, so that to ensure very good visibility at the interference. And so what is the confirmation of the quantum advantage? So this, I should say that this experiment was done with standard at telecom wavelength with standard single photon detectors, indium gallium arsenide photodiodes. And so what is interesting here that you can see, which had the quantum efficiency on the order of 25%, what you see here is the transmitted information as a function of the input size. And there it's important to understand that there is a difference between the performance of the best classical protocol and of the classical lower bound. Okay, so this is not identical. So beating, like we did in this particular work, the best classical protocol is not the same thing, is easier than beating the overall classical lower bound. And this is because protocols actually have these three factors that I was talking to you about. So because it's actually pretty hard to show to show this advantage, and so because to make sure that the soundness, okay, so the result of the protocol when the testing is wrong. And you have to have the probability of winning the test, let's say, of winning the protocol. In this case, depends on the quality of your protocol. So there is a gap actually between the bound and the protocol. So typically, it's not when you close the bound, it means that you have found the optimal protocol. But this is not always easy. And for this problem, it has not been found in the classical case. So what we did in this experiment is that we actually beat, as you see in the zoom here, the classical protocol, and that was with input sizes in the order, as you see, of 10 to the 3, 10 to the 4. 10 to the 3, 10 to the 4 input sizes, where the dark counts of our detector can be neglected. And indeed, we neglected them at that case. Now, if you wanted, as you see, to beat the lower bound, really show that there is no way classically that you can solve this problem with a specific amount of transmitted information, you need to cross this bound. Okay, and for this, as you see, you need detectors on the order with dark counts, basically in the same order of the input. The detectors dark counts that we use for the setup are in the same order of the input size that you will need. So you are kind of lost into the signal, into the dark counts, and therefore that was not possible at the time that we did this experiment. Now, extremely recently, with replacing our previous detectors with high performance, very efficient and very low dark count and nanowire superconducting detectors, it has now very recently been achieved in the lab that we also crossed this bound as well for the specific protocol. And I should say here that this delta factor, which I said before, is on the order of 0.1. Okay, this is the probability of the error in the system. I'm going to conclude with an application to finish this family of results, with an application to a computational problem, even more computer science, sorry about this. So an application to NP complete problem verification. So I'm going to explain a bit what I mean by this. So we're interested here in a quantum advantage for a computational problem that we find useful. So I should say that this is not a sampling problem. So it's not boson sampling. It's not a computational problem that is boson sampling, or the one that Google does with random circuits. You know, these are the type of problems that are typically considered as the candidates for proving the so-called quantum supremacy, right? And they have been used by all the systems, and they are still very good candidates, either in Gaussian regime or in the single photon regime, for proving computational advantage. So the problem that I'm going to show to you here is not a sampling problem where you just want to show that you have sampled properly one from a distribution. It's a yes and no problem. Okay, so it has an answer. It is a satisfiability problem, and our setting is also not a setting, the standard setting for quantum computing, where you have basically a quantum machine, a quantum processor that needs to solve a specific problem in a specific time. We are going to be operating in a prover verifier interactive setting. I'm going to explain what I mean by this, and I'm going to show that we have shown this advantage inspired by the techniques that I just showed to you, and this experimental platform that combines techniques like coherent states manipulation and linear optics and single photon detection, to show this with available technology. So to do this, we used this issue of verification of NP complete problems with limited information. So let me go back a little bit to the basics and explain what I mean by this, to understand why this is important and why these problems are interesting. So this interactive setting is basically what we do. We're in a communication framework. As I said, it's not a standalone machine that needs to solve a problem. We're in a communication setup where we allow two parties, the prover and the verifier, to interact in a predefined manner. And then basically we look at the time that it takes for one of them to solve a specific computational task. And then we see how much time, so this is indeed a computational advantage in the sense of time, okay, that they can use with classical or with quantum resources. A very quick reminder on complexity classes now to remember what is NP. So for those of you who don't remember this, P are problems that are solvable in polynomial time, NP are problems that are solved in polynomial time. Remember that are verifiable, normally NP complete problems are verifiable in polynomial time if the whole solution is given. That's why I'm insisting a lot on this limited information here. I'm going to explain again. Otherwise, it takes polynomial time. It's an easy problem to verify an NP problem. NP complete problems are the hardest problems in the NP class, and they are they contain among the most interesting problems in computer science, and they are all related to each other. So when you make a statement about one, typically it applies to the whole class. And then a specific category of quantum protocols are the so-called quantum Merlin-Arthur protocols, QMA. where it's exactly in our setting where the problems are verified via interaction with a quantum proof. And this is exactly what we're going to do. So we're in this class of QMA problems. So what is the problem we're going to look at? Is the problem that is called 2 out of 4 SAT. Okay, so this is a satisfiability problem where what does it mean? It basically you have n variables, and you make a clause that has 4 clauses that contains at least 4 of the variables, and the 2 out of 4 SAT, it means that at least 2 out of the 4 clauses need to be satisfied for each, so these are parity, that needs to be satisfied in each, at each instance. So the one who looked at this problem is Scott Aronson. So a few years ago, he showed that for this type of problem, he showed that if you make the assumption that the prover, who we typically call in these problems Merlin, sends to the verifier, who we call Arthur, a specific number of proofs, okay, of the solutions to the problem that are all unentangled, okay. The paper is called The Power of Unentanglement, okay. If they are all unentangled with each other, you send square root n proofs, and it's revealing long n bits of information, so you do not reveal all the solution. Otherwise, this would be an easy problem, as we said before, polynomial time problem. Then then normally, classically, you will need an exponential time for the verification, while quantumly, you need a polynomial time. And there you are, you have your gap, your exponential gap that you, for this particular problem, under the promise, as we say in computer science, of unentangled proofs. So what we did initially in theoretical effort is first we took this protocol by Aronson and we translated it into a linear optics platform, okay? So we said, so not the coherent state mapping that I showed you before, just single photons, lots of them, okay? Single photons, and you somehow encode your input to the problem to these single photons. You have loads of them, as you saw, square root n of them, and then we showed that with some permutating these modes and applying interferometric techniques and looking at the single photon detection events at the end, you can checking the satisfiability, uniformity, and symmetry before all these between all these proofs. You can show you can use this linear optics platform for demonstrating the quantum advantage. So now, if you wants to perform this, implement this protocol in practice, you fall in the same problem that we have before. You need hundreds and thousands of these photons to actually demonstrate the quantum advantage. And so that's why we went back to our sampling matching, and we showed again. We showed again that you can use this intermediate, let's say, hybrid platform of encoding in coherent states and checking the single photon detection statistics in a relatively simple setup where it's extremely important to take care of synchronization and this type of techniques and of visibility, of course. You can actually demonstrate the quantum advantage. So this is a relatively, it's extremely important to properly define your protocol. You need to calibrate, and you need to first make sure that Arthur and Merlin agree on when the proof is going to be accepted. You need to find the visibility and transmissivity values that are going to be used for the protocol, and the average number photon of pulse, which is pretty low in these systems. You need to assign as well. You need Arthur to interfere with his pulses with Merlin and properly label the single photon detection events, and then you measure the number of satisfied clauses to accept or reject the proof following quantum advantage conditions, with making sure that the verification takes time linearly, which is the whole point of showing a quantum advantage, and keeping the specific, making sure that the equivalent, that the bits of information that you reveal, that Arthur obtains, is much smaller than the actual number of input, to make sure that in the corresponding classical case, it would be totally infeasible to actually perform this protocol with classical resources. And so I'm not going to go through these details now, but we have formally shown, the first numerically and then experimentally, that this gap is satisfied, and you can demonstrate with the system that you have a quantum advantage for this specific computational task. So again, I repeat, this is in an interactive setting with a simple experimental set. So this is the prover verifier type of protocol. And I should say that these limited knowledge proof systems, this is how they are called originally, they have applications, in particular in server client computing. So for example, you can imagine that the prover is a powerful quantum server that has actually found a solution somehow to a difficult problem and wants to communicate, wants to prove, wants to show to the verifier that he has found the solution, but without revealing much information about it, right, to the client. So this is a case where this could be used, or because of proprietary knowledge, for example. And then all this start from a more cryptographic point of view. All these types of limited knowledge proof systems are used for techniques for identification, authentication, blockchain, etc. So for the moment, it remains, of course, a bit a theoretical the interest, but there is a specific of these satisfiability problems are interesting for many applications. So I'm going to conclude here. I hope I have shown to you that there is a big number, that there is a big world in the protocols in quantum communication and computing, and there is a very rich world as well at the interface between physics and computer science that can take advantage of advanced photonic experimental platforms. We can actually demonstrate advantage for useful tasks even now, while at the same time advancing towards more and more complex systems. And my hope is that we gain knowledge and get feedback from this type of implementation, protocol implementations, to target better the developments that we need in our experimental photonic systems, to actually demonstrate later this type of protocols for more and more difficult applications. So I would like to thank my colleagues here that participated specifically in the last part, in the biggest part of this talk, and thank you very much for your attention.